Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 9, Section 3, titled Angles of Elevation and Depression. By the end of this video, you will have reviewed recent lessons describing angles of elevation and depression. Discussions will include using angles of elevation and depression and identifying angles of elevation and depression. You will also review a couple real-world problems that require the use of possibly both angles of elevation and depression. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find the video to be helpful. Thank you. Okay, to get started, we'll look at a couple definitions. So what is an angle of elevation? An angle of elevation is an angle measured above the horizon line. So if you're looking straight out in front of you and you tilt your head up, you're elevating your sight. That angle created as you look up is an angle of elevation. An angle of depression is just the opposite. The angle of depression is an angle measured below the horizon line. So if you're looking straight out and you start lowering your eyes, the angle created while you're lowering your eyes is an angle of depression. Objective 1. Using angles of elevation and depression. Suppose a person on the ground sees a hot air balloon gondola at an angle of 38 degrees above the horizontal line, a horizontal line. This angle is the angle of elevation. You can see it in the picture. This lady is standing on the ground, and there's a horizontal line which would be at her eye level. And then there's the gondola of this air balloon hanging from the bottom of the balloon and creating another horizontal line. So we can call those parallel horizontal lines, right? So for her, the 38 degrees looking up is an angle of elevation. And from the gondola, the people in the gondola looking down at her would be an angle of depression of 38 degrees. So that at the same time that a person in the hot air balloon sees the person on the ground at 38 degrees below the horizon line, this angle is an angle of depression. So as we just said, examine the diagram. Let's look at it. The angle of elevation is congruent to the angle of depression because they are alternate interior angles. Okay? Example 1, identifying angles of elevation and depression. So describe each angle as it relates to the situation shown. So we have this hiker on the side of a mountain or side of a hill here, and he's creating some angles, and there are some being created by the horizon and such. So it says angle number 1 is what? Angle 1 is an angle of, let's look at it. Angle 1, we see it up at the peak, up here at the tip, up here at the top of this mountain over here. Okay, so angle 1 is the horizontal line is if you were standing on the peak of that mountain looking out. So that's the line going across the surface here. You see that? So angle 1 is the angle of depression from the peak. And that person, if the person standing there, is looking down at the hiker. So it's an angle of depression. And on the other hand, we can look at angle 4 for B here. Angle 4 is an angle of elevation, and that's from the hut. The hut is down here on the ground, way down here on the bottom, creating angle 4 with the Earth's surface and looking up at the hiker. Okay, that is an angle of elevation. You're looking up, elevation, looking down, depression. Okay, example 1, check your understanding. So why don't you take some time for yourself and look at this diagram. It's the same one we were just looking at. And two problems, A and B. It says angle 2. So as we described the other one, what is angle 2? How would you describe angle 2 in problem A? And how would you describe angle 3 from problem B? Looking at that same diagram that we were just looking at. Go ahead, take your time. Pause the video. When you come back, we'll discuss it further. Okay, I'm assuming you've taken your time and you've looked at it and you've kind of understand what you're looking at here. So it says, describe each angle as it relates to the situation in example 1. Well, example 1 is what we're in, and the picture was brought in from the previous slide. So I'm sure you've got the angles correct. So angle 2, what is that? Describe that. Describe that. Well, I would say that angle 2 then is from the hiker's point of view. The hiker is viewing the point or the peak of that mountain in the distance. And that's an angle of elevation because he's looking above his horizon line, which is eye level, up to the peak. So he has an elevation that he's looking up, and it's angle 2 is the formation of that elevation, that angle from horizontal, then drawn up toward the peak. And in B, it's angle 3. Angle 3 is an angle of depression, and it's looking from his line of sight horizontally down to the hut. So angle 3 is an angle of depression from the hiker to the hut. Okay, example 2. It's a real-world problem. That says to find the height of Delicate Arch. That's the name of that arch. It's in Arches National Park in Utah. A surveyor levels a theodolite at the bottom of the arch. Well, the theodolite is this instrument that the surveyor, this right here is a theodolite, and it's an instrument that surveyors use to measure angles and when they're doing distances and that type of stuff. Very accurate, very accurate. So they're saying that she levels it, which means she gets a horizontal line that runs under, that she's pointing at, that's running underneath the center of the arch. Okay? Theodolite from the bottom of the arch. From there, she measures the angle of elevation to the top of the arch, and that's where she gets 48 degrees. She measures this angle right here, 48 degrees to the top of the arch. She then measures the distance from where she stands to the point directly under the arch. That's where she gets the 36 feet. So she measures from where the theodolite stands to directly underneath the arch. And as she measures that off, that distance ends up being, oops, I got to get this line that's goofed up on me. She measures that, and it ends up being 36 feet. Okay. So now what does it say? Directly under the arch, the results are shown in the diagram. What is the height of the arch? They want to know how tall is that arch. Well, so what do we know? We see that we have the 48-degree angle. We have x is the opposite, and 36 is the adjacent. So opposite and adjacent gives us tangent, and it's 48 degrees. So we can write the equation here that the tangent of 48 degrees is equal to x, which is the opposite, over the adjacent, 36. Okay? And when we run that, when we solve for x, we just take both sides and multiply both sides by 36, and we get x is equal to 36 times the tangent of 48 degrees. Well, if we run that now in the calculator, because you're going to need a calculator to get the tangent of 48 degrees, you type in 36 times the tan 48, and you're going to get for 36 times 1.110612 using your calculator. And you see here it's approximately, we're talking about approximately, because we no longer, x is no longer known because of this line here. The sine of 48 degrees, or the tangent of 48 degrees goes on forever. Anyway, so then x is approximately 39.982051 feet. That's the height of the arch. But is it the complete arch? Well, no, because we also see that they pointed out, and you'll see this in a number of problems as you go forward in mathematics, that you've got this piece right here, this leg standing down. And what is that? That's because or where the height of the theodolite is from the ground, is that same 5 feet. So whatever the height you got here for this line, which is from the horizontal line coming from the theodolite to the top of the arch, you have to add the 5 feet to it. So therefore, it says x is approximately 40 feet, right? To find the height of the arch, add 5 feet to the height of the theodolite. Since 40 plus 5 is 45, Delicate Arch is about 45 feet high. Okay, example 2, check your understanding. Why don't you go ahead and stop the video, look at this problem, and see if you can solve it on your own. I'll wait for you. What you're looking for is you sight a rock climber on a cliff at a 32-degree angle of elevation. The horizontal ground distance to the cliff is 1,000 feet. Find the line of sight distance to the rock climber. That's like looking, how long is the line looking up at the rock climber? So go ahead and take your time, look at it, and then when you come back, we'll try it together. Okay, I'm going to assume that you've tried it and you're back and we're going to do this together. So it says you sight a rock climber on a cliff at a 32-degree angle of elevation. So I'm going to draw we got the ground, right? We have a cliff, all right? We have a rock climber hanging on the cliff, and you are way back here, 1,000 feet. You're 1,000 feet from the cliff, and the rock climber is being observed at an angle of 32 degrees. And we're trying to find x. The distance from you, I'll draw a little picture of us standing there, you, okay? Picture standing there looking at this person, okay? I guess I could have drawn it with, let me draw it a little more, well, since I'm drawing pictures of people, which aren't very good anyways. You are looking at them. We'll have to play that same game. Your eyes are right here, right? And we're going to assume that you're 6 feet tall. So when we come up with an answer, I'm going to come up with an answer that is going to add 6 feet. But so you're looking from here, you're looking straight out 1,000 feet, and you're looking up at an angle of 32 degrees. And now we want to do is find x. And so we know the angle. We know a side adjacent to the angle. We don't know the side opposite. And we also know what we're looking for is the hypotenuse. And when you have adjacent and hypotenuse, you're looking at cosine. So what we're looking for is the cosine of 32 degrees is equal to 1,000 or 1,000 over x. So we want to solve for x. So we're going to swap these two, and we're going to say that x is equal to 1,000 feet divided by the cosine of 32. Okay, and that answer is what? Let's see, I can get my calculator here. I'm going to say the cosine of 32 degrees is, I'm going to write it in here. So it's x is equal to 1,000 divided by 0.804. No, not 804, excuse me. 804. I looked at that incorrectly. 8 back here. 848. 848. I'm making more mistakes than I know what to do with here. Sorry. 848. Let's get it right, Bob. Okay, 848. 048. 048. We'll stop there. So that's the cosine of 32 degrees. And now we've worked the problem, so we're going to take 1,000 and divide it by this 0.8, whatever this number is. So it's going to be 1,000 divided by 0.848804. And we come up with an answer of x equals 1,178.128. That'd be enough feet. Okay? That's what I come up with. 1178.1. So I must have cut short because my answer is a little bit rounded. Is it 1179, 1178? Yeah, I round up. Anyways, it's close enough. You see, this is an approximate answer anyways. This right here is approximate. Okay? So we're looking at an approximate answer of x being equal to 1,178 or 79 feet. And if we add our 6 feet, you're going to get 1,184 feet if you're going to add on for your eyes to the ground. Okay? Okay, example 3, it's a real world problem. To approach a runway 17 of the Ponca City Municipal Airport in Oklahoma, the pilot must begin a 3-degree descent, that's the glide path pointing down at an angle of depression of 3 degrees, starting from an altitude of 2,714 feet, and that's in above sea level, the 2,714. The airport altitude is 1,007 feet above sea level. How many miles from the runway is the plane at the start of the descent? So they want to know how the distance of the plane from the runway. That's this distance here. Okay, that's what they're looking for. At the start of when he starts the 3-degree down angle. Okay, the airplane is at 2714 and the airport's at 1,007. You have to subtract them, and then you'll know this height right here from here down to the ground. What this distance from here is your 1707. 1707 right there. Okay, that's that height. And we know that we have a 3-degree angle, and we know that we're given one of the legs of this angle, and we want to find the hypotenuse, because we should know that this is a 90-degree angle right here from this horizontal line right here. The line that the airplane's flying on, horizontal with the earth at the airport level. There's a right angle. So we're looking for the hypotenuse, and we have a side which is opposite of the 3-degree. It's out here. This is the elevation right here. We have that, which is 1701. I drew it back here so you could see it, but this line can be brought over to here. So that means that we have the opposite, and we need the hypotenuse. So in order to do that, we're going to take the sine of 3 degrees right here in the problem, and we're going to say 1707, that's this distance from the ground to the airplane, divided by the hypotenuse, which is x. We're going to call that x. Okay? And once you do that, then you're going to use, this is the sine ratio we're using. So then we're going to solve for x, means we have to swap the sine of 3 degrees and x around. So we're going to get x is equal to 1707 divided by the sine of 3. And that's solving for x. Then x is equal to what? What is 1707 times the sine of 3 degrees? Well, when I run it on my calculator, I ended up with approximately 32,676.799 feet. That's the length of the hypotenuse running down to the airport. Well, if we take that and divide it by 5,280, that's the number of feet in a mile, we'll know that we have 32,767.799 divided by 5,280. We're going to get approximately 6.1773105 miles. So the airplane is going to start its descent at about 6.2 miles from the runway at the start of the approach. Okay? Okay, example 3, check your understanding. We'd like you to do this one on your own. An airplane pilot sights a life raft at a 26-degree angle of depression. The airplane's altitude is 3 kilometers. What is the airplane's surface distance? D, the distance D, from the raft, this life raft. So that's the airplane along the water's level, not the glide path, so to speak, right? That previous problem, we were talking about the glide path going in. Now we're talking about the distance on the ground from the plane to the raft. You go ahead and try to solve it. I'm sure you will. And when you come back, we'll go over it together. Okay, so now you're back. An airplane pilot sights a life raft at 26-degree angle of depression. The plane's 3 kilometers in the air. What's the plane's surface distance from the raft? Well, we have a picture of the plane here with a raft. The distance we're looking for is the waters at the water's level, right? We're 3 kilometers in the air. We have a 26-degree angle, right? 26-degree angle right here. There's our 20. Here's our 3 kilometers that we're in the air, and we're looking for D. So what do we have? We know that we have right here 26. We know that this is 26 down here too, because of parallel lines, right? And the opposite interior angles of a parallel line, right? Divided by a section. Okay, so what we're dealing with here, though, is we want D. We have the 3 kilometers, so that's the opposite and the adjacent of the 26 degrees. So we're looking at tangent, opposite and adjacent we have. What we're looking for is the adjacent. So we write this as the opposite is 3, so I have 3 kilometers right here. So the tan of 26 degrees is 3 divided by D. We're going to solve for D, so we're going to swap D and the tangent of 26. We've done that before. So now D is equal to 3 divided by the tangent of 26 degrees. And using the calculator, you're going to find out that D is approximately equal to 6.150911. That'll be feet we're dealing with here. Oh, no, excuse me, kilometers. Okay, kilometers. Sorry, I said feet. Kilometers. And that, if you round it to a more respectable number, because this is it's an about anyways, right? It's an estimate. So D is approximately equal to 6.2 kilometers. That's the distance from the life raft.